homogeneous spaces. There's a number of them, I call it. And there are maps, there are algebraic maps, there are rational maps going down. And these maps are height increasing. Okay, they are quadratic maps, so the height doubles because it's logarithmic. Okay, so the maps are about quadratic, the equations are quadratic, so the height of the x-coordinate about doubles when you go from here to here, but that's good news because going from here to here, it halves. Okay? So you can do this, in fact, as many times as you want. Once you are here, you don't find the points here, you can do a descent and find the people who do the descent, the descent children. Okay, so this is the father or the mother, and these are the children, and then there are more children here, more children here, more children here, and so on. Okay. The problem is that I think in Magma you can do 2 layers, but nobody knows how to program farther layers of the algorithm. And the equations just get too difficult to write down. Okay, so these are called homogeneous spaces. And there are maps going down, but how do I know that the points are going to be there? It turns out that if you have a point in here, it always belongs to one of these. I don't know which one a priori. Well, actually, if I know the point, then I can tell you we'll have a map back, and it's going to show up in there. So once I have a complete list of the homogeneous spaces, I can look through all of them, find points, send them back, send them down, and if I'm somehow able to cross out, by whatever means, all of them, either finding points or proving there are no other points, then I know I found all of them. Okay, so that's the idea of the descent. As I said, there are several flavors of descents. The very most basic one is called a full to descent. And I'm going to do a poor job at describing it here. It's explained in more detail in chapter 2 of the notes, and there are actually some proofs in that chapter. So full to descent means that I'm going to do it for elliptic curves that have a full to torsion defined over Q. Okay, so these EIs are going to be integers and distinct. Okay, so how are we going to find points? Well, take one point. Suppose there is a point. Then what has to happen, this is just a very naive explanation of what has to happen. Well, what has to happen is that these 3 multiply to be a square. So there may be, there's going to be, this number itself is going to be some number times a square. So the square part of this number is going to go into here, that's good. What I'm worried is about the square free part of this number. The square free part and the square free part, those 3 square free parts have to multiply to a square. Okay? So let's see where that goes. So this should be the square free part times a square. And what I need is that all 3 multiply to be a square. Okay? If that's the case, let's multiply this equation both sides by delta 1, delta 2. I want to eliminate one of the deltas. So if I multiply both sides by delta 1, delta 2, I get a square there, that's good. And a square times delta 1, delta 2. So what that says is that modulo squares, delta 3 is just delta 1 times delta 2. Or in other words, if delta 3 is delta 1, delta 2 times the square divided by delta 1, delta 2 square, this is a square which can be thrown into W. This is a rational number, this is a square, so it can be put in W, right? So I'm going to actually substitute delta 3 by delta 1, delta 2, and it's all the same. Okay. So now I have E, that equation, x naught minus 1 is delta 1 U square, x naught minus E2 is delta 2 V square, and x naught E3 is delta 1 delta 2 W square. Okay. And if you subtract equations, now I want to get rid of the x naught here. What this brings me is to what I'm going to call C of delta 1 delta 2, and it's E3 minus E1 is delta 1 of, I'm going to replace now, this is a variable, that's what I want to find. Okay. So you see, for each delta 1 and delta 2, I have one of these spaces. But if I started with a point x naught, y naught, if I start with an actual rational point, I can carry this through and find for you what is delta 1 and delta 2, and that will actually give me a point in here. Okay? So EQ actually maps to C delta 1, delta 2 for some delta 1, delta 2, or rather a point we know what the map is. X naught, Y naught maps to x naught minus E1, comma, x naught minus E2 modulo the square. Okay? Or rather to, not to that space, but to sort of like the spaces of delta 1, delta 2. Like in what delta 1, delta 2 I'm going to find my point is given by that map. Okay? All right. So how do we use that in our favor? But maybe I lost too much information here. I subtracted. I did some algebraic mumbo jumbo, and maybe I lost my point here. Can I go back? If I find a point here, can I go back and find a point on the elliptic curve? It turns out I didn't lose any information, and there's a map also from any delta 1, delta 2, from any of those spaces. I can go back. If I have one of these points, it maps to the point A1 plus delta 1 x naught squared, comma, delta 1, delta 2, x naught, y naught, z naught. You can check if that works. Okay. Very good. So, yeah.
So since your two functions are rational, can I use the rounding equation, like move it to 0 and lambda?
You can, are you saying that I can always choose E1 to be 0?
Yeah, since you're rational, right, you can compose it with the algorithm P1 0 and
that doesn't work over Q. It doesn't, that automorphism,
yeah.
you can't do that for any elliptic over Q and get a lambda that is in Q. Yeah.
Wait, but the two torsions are over Q.
The two torsion points are over Q, but when you do that transformation, the lambda doesn't need to be over Q. It's a good idea, but it doesn't quite work. You have to go to an extension And that's something that is used many times. That's called a Legendre form of the elliptic curve. And you can do that to do other things, but you have to keep track of what extension you went to when you did that change. Okay. So we have a map. It turns out this also forgets about two multiples, so by 2 of a point. It turns out this forgets about those two. So it's a map, yes. This modulo squares. Meaning that if x naught minus 1 is 18, that's what, 2 times 9, so I keep a 2, and my delta 1 is 2. So it turns out that the map works best. There is some kernel in the map, and the map is things that are twice a point, which is fine by me. I want the generators to survive, and the generators will survive the map. The problem is that 2 torsion points survive in this quotient, so they will be mapped also. There will be also, we'll have to find where they are and make sure we don't confuse them with generators of the rank. But there's a map to, I'm going to call it delta, to some gamma delta. What's the image? So gamma delta is the space of delta 1, delta 2s. Okay, where these deltas are integers, non-zero integers that are square free, and there are a lot of numbers that are square free in the integers. Just take any prime, that's one of them. So I want to restrict that, and it turns out you can restrict that. The numbers that appear there, this is some corollaries. This is also explained in chapter 2 how this comes about. But the numbers that appear are if P divides delta I, then P divides the discriminant of E, which in this case is just the triple product of all the differences. Okay, the map is defined like in here, that map, and this map is injective, and it is a homomorphism. So it is a homomorphism. That means that, well, what is the group structure here? You can multiply two numbers and then remove squares, and that will bring you back to the set. And so you can multiply pairs and see where they go. I'm not sure I'm going to have time today to do one example of the descent. We'll do tomorrow. But in particular, if you've had abstract algebra, you know these consequences, but it's just it's good to point out what's happening. So what I want is, I don't know this, and I want to find generators of this. So I want to go here and see what is in here. I can calculate this now, and it is finite now because there's only finitely many primes divided by the discriminant. It's a finite group. I want to know what comes from here. So what I can say is, for instance, since it's a homomorphism, if a pair delta 1, delta 2, and a pair delta 1 prime, delta 2 prime are in the image, then their product is also in the image. Okay, so there's a lot of restrictions. And all the possibilities. So if delta 1, delta 2 is in the image, but delta 1 prime, delta 2 prime is not in the image, then their product is not in the image. Okay? So I will exploit that as soon as we find something that is in the image, we find another thing that's in the image, you can do the products and find other things that are in the image. Once you find something that is not in the image, you can also find other things that are not in the image. And what this means is, so in terms of spaces, it means that if you have a point here and it goes here, if another point and it goes to another of those spaces, it means that if one of these spaces has a point and another one has a point, when you multiply those deltas, that gives you another space that also has automatically another rational point. That will give you a point down, which is not actually interesting as a point for us because it's the sum in the elliptic curve will be a point that is the sum of the two you have already found. Okay? But it gives you a way to narrow down what's possible. And so let me just set up one example. Yeah.
When you say he divides the value, like both yes or anyone?
This?
Yeah, the implication. Like he divides the other one.
What I'm saying is what delta I for I 1 or 2. So what delta 1s can happen are restricted by these conditions. And what delta 2s can happen are restricted by these conditions. So it is really, if you define these numbers, this is the product space of two identical sets, right? So what happens is that if you have e to be y squared equals x cubed minus x, I'm going to run it too high. Then this is x times x minus 1 times x plus 1. And I can take e1 to be 0, e2 to be 1, e3 to be minus 1. The delta, the product, like this product, is minus 1 times 2 times 1 is minus 2. And the possible pairs are the possibilities are, well, it can be plus or minus 1 or plus or minus 2. That's it. Okay? So there are 4 times 4, there are 16 possibilities. So this thing has 16 elements. And what we're going to do next time is check all of them, all of the possible spaces, because if there are rational points on the elliptic curve, they are in one of those 16 spaces. So we're just going to make a map of all the spaces and check which ones have points, which ones don't. We'll find that only the torsion points are being, they show in the spaces. There are no others, so the rank is 0. There are a couple of examples like that in the notes with more exciting rank 2 or so. So we'll do that next time. And